Hello everyone, my name is Natasya Indah from 12E, currently taking the AP Physics 1 course in the academic year 2023-2024. And in this video, I will be sharing about how you can derive equations from simple harmonic motion. Before we begin, I will briefly introduce you to what simple harmonic motion means to those who aren't familiar with it. Here, simple harmonic motion means a repetitive back and forth motion in an object where it is displaced from their equilibrium position, where the object itself would experience a restoring force that is proportional or opposite to the displacement. Now, how are they relevant? The simple harmonic motion is actually relevant in various physical systems such as springs, pendulums, or even vibrating strings such as guitars. These systems are relevant to the simple harmonic motion because it exhibits a oscillatory behavior where the force of the object, specifically the restoring force, will be directly proportional to its displacement from equilibrium. Now, how can we apply this to the real world? The simple harmonic motion equation is usually used not only for physics but also for biology, engineering, and other fields where oscillatory motion plays a significant role. For example, here, physicists usually use these equations to study the behavior of particles in potential wells and molecular vibrations, where engineers use it to design structures like bridges and buildings to withstand vibrations and oscillations. Lastly, biologists would usually use simple harmonic motion equations to investigate biological systems like the beating of the heart or other concepts that would use simple harmonic motions. Before we begin calculating to derive the equation itself, we usually use this law, which is the Newton's second law, where force is equal to mass times acceleration. Here, F means the net force acting upon the object, m means the mass of the object, and lastly, a is the acceleration of the object. Now, not only that, the other law that we usually use for this is the Hooke's law, where F is equal to the negative k times x. Here, F is actually the force exerted by the spring, or usually the restoring force, and k is the spring constant, and x is the displacement from equilibrium. Now, from these two laws, we can see that both of the laws actually use the exerted or net force of an object, and we can actually combine them together. So F is equal to m times a, or F is also equal to negative k times x. Now, in simple harmonic motion, we should also understand that F, as in the restoring force, will always be proportional to x, which is the displacement towards the equilibrium. Now, this means that F and X will always be in the opposite direction of one another. In simple harmonic motion, we can see here that the Hooke's law actually starts with a negative sign. This is to show that the restoring force, as in the F, will always be proportionate to the X, where over here you can see that the equation is negative. And here is an example where the pendulum here has a restoring force and a displacement. Specifically, the pendulum's restoring force will be like this, and oppositely, the displacement from equilibrium will be like this. Now, before we actually start calculating to derive, this is also several things that we should keep in mind, where here the omega is equal to the square root of k divided by m, and t, or period, is equal to the square root of 2 pi over omega. Now, moving on to the actual calculation, we know that the restoring force, or F, is always proportional to x, which means that they're always at the opposite direction. And since we can combine Newton's second law and Hooke's law, we know that F is equal to ma also equal to negative kx. So from here, we can actually derive a, or acceleration, where the second derivative of a is equal to d squared over dt squared. So if we plug this in back to that equation, f is equal to m times d squared over dt squared equals to negative kx. And from here, we can divide both sides by m. So here, it becomes d2 over d2 squared equals negative k over m x. Since we also know that k over m is the angular frequency, or omega, we can plug this in again. So d squared over dt squared is equal to negative omega times x. So this will be the derived equation. Now we are going to simplify the equation. Since before we know that a is equal to d squared over dt. We also know that a is equal to dv over dt, which is the first derivative. Now here, if we plug it into the equation, it becomes dv over dtx plus the omega of x. Now here, we need to use the chain rule for this part. So this is going to be dv over dx times dx over dt. Now, we should also know that dx over dt is equal to v. So if we plug this in again to the equation, it's gonna be dv over dx, which is this part. Times v plus omega x. Now here, if we move dx to the right over here, it is going to be v dv plus omega x dx, or v dv equals to the negative omega x dx. Now what we're going to do next is to integrate both sides. So first, we're going to do this. So if we integrate v times dv, the results will be half v squared. And for the second one, if we integrate negative omega x dx, the results will be negative omega times half x squared plus constant. Now, if we go back to the pendulum before in the slides, we know that x, or the displacement, is equal to a, which is amplitude. And we also know that when the amplitude is at its maximum point, then the velocity will be equal to 0. And c, which is this constant over here, is going to be half a squared and omega squared. So now if we put this all together, it's going to be, we integrate v dv plus the integrate of negative omega x dx plus constant, which is half a squared omega squared. And the results for this before was half v squared plus negative 1 over 2 x squared omega squared plus half a squared plus omega squared. So from here, we can actually cross out all of the 2's. So the results will be v squared plus x2 omega squared plus a squared plus omega squared. And if we factor this out, this will be omega squared. Sorry, this is negative. Negative x squared plus a squared. So from here, we can square root them. So v plus omega to the square root of negative x squared plus a squared. And this is also equal to v equals omega, the square root of negative x squared plus a squared. So this is the way you can find velocity. But what we're trying to do here is to find the displacement, or x, which is over here. So what we can do there is go back where we know that v is equal to dx over dt. And from here, if we replace it, it'll be dx equals omega to the square root of negative x squared plus a squared. And we can add dt over here, because if we do this, we can move it over here. So now, since there's an x over here, we can move the x to the left, which will be dx over the square root of negative x squared plus a squared equal to omega dt. Now again, what we can do next is integrate both sides. So first we're going to integrate dx over negative x squared plus a squared, which is going to be sin negative 1x over a. And for the other one, the integration of omega dt is equal to omega t plus phi, which is phase constant. So we're gonna write here phase constant. And so if we plug this into an equation, sin negative 1x over a is equal to omega t plus phi. And if we move the sin to the right, it's going to be x over a equals sin omega t plus phi. And if we move the a to the right, then it's going to be x equals a times sin omega t plus phi. So this is the results, and this is how you can find the displacement from the equilibrium. Thanks for watching.